Welcome to the support video for Topic 2, Sets and Predicate Logic, Part 1. In this video, we'll be looking at what a set is and how we would define a set. We'll be covering quite a few symbols and definitions, so you should expect to pause parts of this video or watch it more than once. So, what is a set? A set is a collection of elements. These elements are distinct and exist unordered within their set. Okay, so what's an element? An element can be just about anything. We might have a set of shapes, or animals, letters of the alphabet, or even a set of other sets. Were we to define mathematics more restrictively, we might talk about sets of numbers, or sets of logical propositions, but sets can contain anything. A set is usually denoted by a capital letter, and might be defined like this. Let A be 1, 2, 3, 4, 5. This is one of two ways we'll be looking at defining a set. We'll be looking at both in this video, but let's stick with this one for now. What we have here is a finite set. It is limited in size, containing 5 elements. Even if it contained 1,000,000 elements, it would still be finite, because it would still be limited in size. Of course, defining a set of that size in this way would be time-consuming, so we have something of a shortcut. If we have an ellipsis within the set, think of it as meaning and so on. So 1, 2, 3, and so on, 999,999, 1,000,000, is a finite set of 1,000,000 integer elements. An ellipsis at the start, or the end, or both, denotes an infinite set. Infinite sets are not limited, but they do not necessarily contain every possible value. For example, this infinite set doesn't contain 0, and this infinite set doesn't contain 5, although it does contain all negative integers. This set, with an ellipsis at the beginning and another at the end, contains every integer value, positive, negative, and 0. We're going to look at a few propositions now, in order to illustrate some of the symbols used in set theory. A proposition, if you remember, is a statement that is either true or false. This proposition means 5 is a member of set A. Well, it either is or it isn't, and that depends upon the set. If this were our set, our proposition would be true. With this set, the proposition is false. Here's another one. This means that 5 is not a member of set A. So does this. Again, it depends upon the contents of the set. If we're saying that 5 is not a member of this set, that's false, because it is a member. If that's confusing, it's because it's a kind of double negative. 5 is not a member of this set. You'll get used to it. This way of defining a set is called definition by enumeration. We can also define a set using set builder notation. This can follow several slightly different formats. Let's say we want to create a set called B, consisting of the integer values 1 to 5. If we were to define this using enumeration, we would do so like this. Using set builder notation, it might look like this. Here's our set's identifier, and here are the criteria by which elements are members. A number, which we'll refer to as x, can be a member of this set if it is greater than 0 and less than 6. This vertical line means where. So, x is a member of set B where x is greater than 0 and x is less than 6. Acceptable variations within this notation are minor. We might use the word and instead of the conjunction symbol. We might use a colon instead of a vertical line. We might reorder the contents of the expression slightly, placing the membership operator to the right of the where symbol. So all of these are valid ways to define a set containing the integer values 1 to 5 in a set identified as B. You might notice something strange about this set. Members of this set are greater than 10 and less than 10. There are no numbers that are both greater than and less than 10, so this set is empty. Its cardinality is 0, and this is denoted like this, or like this. This set contains numbers that are less than 7 and greater than 5, meaning this set only contains the number 6. It's quite acceptable for a set to contain a single value and still be considered a set. This would actually be known as a singleton set, with a cardinality of 1. Earlier in the video, I said that elements within a set are distinct. So what does that mean? Let's say we have this set. How many elements are there? It looks like 7, but there are duplicates. The number 2 is present twice, and the number 4 3 times. Really, our set looks like this. The elements are now distinct. No two are the same. And the cardinality is 4. We would write this like this. The set D is not equal to 4. It contains 4 elements. Just a few more symbols now. This one means is a subset of. A subset is a set that is wholly contained within another set. If this is set E and this is set F, set E is a subset of set F. Set G is not a subset of set H because one element within set G is not present within set H. We could use this symbol here, which means is not a subset of. What about this? Yes, set J is a subset of the identical set K. This means that K is a subset of J as well, and any set is a subset of itself. We can also say that J and K are equal, whereas G and H are not equal. Thanks for listening. This last slide contains all symbols used in the video as well as all terms. If you're unclear on any of these, please re-watch the video. Later material in this module requires you to understand these. You should still be aware of these from a previous video.